All right, so the goal today is to go through a bunch of different possible topics for research for the summer. So the first is going to be an introduction to random matrix theory. All of these slides I will post online. I've already emailed them to you. If you did not get that email, that means you cannot handle about a 30 megabyte message. I will probably not go into the L functions at the end over here because that will be a different talk. There's a lot of ensembles. I'm not going to go through all of them. There's a limit to how much you want to see at one point. The idea is to give you a sense of how these problems are done, what kind of techniques you need to use, and then if you're interested, you can read about some of the other stuff, about the specific stuff for each system. Okay, so first, introduction. So the goals of this is to try to figure out what's the right object to study, how do you find the right scale. The right scale is often extremely difficult. And then what tools and techniques do you need to do the calculation? Interestingly, you often use very different tools in random matrix theory as you do in number theory. But you get the same answer, which is wonderful because it allows you to check your work, or at least conjecturally to check your work. So let's look at a couple of things. So a huge amount of my research can be formulated as the following. I have some system and I observe events, T1, T2, T3, and I want to know what rules govern the spacing between these events. So depending on who you are, you might study different things. If you're a nuclear physicist, you'll look at energy levels of heavy nuclei. You could look at eigenvalues of matrices, zeros of L functions, summons and Zeckendorf decompositions. How long do you have to wait for the next summoned? Lots of other things you can wait. Do you know which company is really good at understanding wait times? As soon as you hear it, it's obvious. Nope. Google's probably not bad. Disney is phenomenal at understanding wait times and estimating just how long of a wait people will have in a given situation. They want to have accurate estimates for people at the amusement park. Do you think they want to overestimate or underestimate waits? Over, because it's very bad if you tell someone it's going to be a 15-minute wait and they wait for 20 minutes. If you tell them it's a 20-minute wait and they wait for 5 minutes, mentally they were prepared to wait longer. So Disney does a lot of very complicated things as well as very simple things to understand how long between events. All right, so today we'll concentrate on the ones in red. All right, so the three things we need to do for all these systems is determine the correct scale, develop an explicit formula relating what we want to study to something that we understand, and then we need to develop some kind of averaging formula to work with the object. So we talked a little bit about this with the eigenvalue trace lemma yesterday. Interestingly, it can take a lot of work to figure out what the right object is to study. This is where number theory and combinatorics interact, and depending on what you look at, it's going to be a lot easier or a lot harder. And we talked a little bit yesterday about how this shifts where the work is. It's often not a bad idea to spend some time thinking which is the object that will have the good expression, that will have something that will make it easy to compare. Okay, so a quick review to make sure we're all on the same page for eigenvalues. Z is a complex number. We can write it as x plus iy. I is the square root of -1. You're an eigenvalue eigenvector pair. If AV is lambda v, lambda is allowed to be 0. The eigenvector v is not allowed to be 0. If you took a linear algebra class, you've probably calculated eigenvalues by using the determinant formula. This is a criminal way to calculate eigenvalues if it's a large matrix. The determinant formula is horrible. There's a lot of really good numerical techniques to estimate eigenvalues. If you have a complex Hermitian matrix, that means A equals AH, so the complex conjugate transpose, then all the eigenvalues are real. And this is extremely nice. You can then talk about them as a spectrum of an operator. So your energy levels of a nucleus should be real numbers. The length of a vector is just basically the dot product, but if you have complex entries, you have to be a little bit careful. The vector 1i dotted with 1i would be 0. It would be 1 squared plus I squared. So when you take the dot product, you take the complex conjugate of one of the two terms. Here's just a simple calculation. I'm not going to go through it, that if you have a real symmetric matrix, it should be real symmetric, not just real, then the eigenvalues are real. And if A is complex Hermitian, the eigenvalues are also real. It's a similar calculation. All right. You might have seen the spectral theorem. If I give you a nice real symmetric matrix, I can change basis with an orthogonal transformation, and in this new basis, the matrix is diagonal, which is really nice. It tells you basically it's just a bunch of stretches or compressions in the different directions. Okay, so classical random matrix theory done with many, many students over the years. This is a subset probably from about 4 or 5 years ago. All right. How many of you have done physics? All right, so if you have 1 point mass in the universe and nothing else, it's trivial. If you have 2 point masses in the universe and nothing else, it's trivial. If you have 3 point masses in general configuration in the universe, we no longer know how to solve it in closed form. So imagine how much worse it is when you have something like uranium with over 200 protons and neutrons and a far more complicated force than gravity. So Wigner's great insight was to basically say, screw this, let me just write down some kind of random system to approximate what's going on. So quantum mechanics can be reduced to the following nice equation. HCN is ENCN. So H is your matrix, and the entries will depend on the system. En are your energy levels, and then Cn are the energy eigenfunctions. There's only 2 small things that prevent this from being done in an introductory linear algebra class. The first is H is infinite by infinite, and most of the time you look at finite by finite matrices. And the second is we don't know any of the entries of H. But other than that, it's perfectly fine to do in a linear algebra class. So the question is, how do you handle having an infinite matrix where you have no knowledge of any of the entries? Well, you have knowledge of the structure of the matrix. Maybe it's complex emission, maybe it's unitary, maybe it's real symmetric. And what Wigner's great insight was to go back to statistical mechanics. So for simplicity, let's imagine all the air molecules in the room travel at the same speed, and they either go left or right. And you want to calculate some thermodynamic quantity such as pressure. I need to know how many molecules hit the board in a certain amount of time. If I wanted to actually do this calculation for the room, this would be beyond anything we can do computationally for the foreseeable future. Anybody know roughly how many molecules there are in a mole? 10 to the 23rd. All right. Do we have more or less than 1 mole in this room right now? A lot more. So even if it was just 1 mole, that's 10 to the 23rd objects to study. And each one of them will probably have 6 coordinates. It's x, y, z position, and then it's vx, vy, vz, it's velocity. So this is an extremely bad system. But Wigner's great insight was the complexity actually helps us. Don't try to solve what's going on for this actual system. Calculate what it would be for every possible system, weight each system by its likelihood of happening, and then calculate the system average. And then you cross your fingers and you pray that a central limit theorem emerges, that a typical system will be close to the system average. And it turns out this does a really good job. So what Wigner did is said, well, let's look at a large n by n matrix with n going to infinity. Let's choose the entries randomly from a nice distribution. And let's calculate the energy levels, the eigenvalues for this specific matrix, weight it by the probability we chose this matrix, and then move on to the next one. And the hope is that the typical system will behave like the system average. So to do things really explicitly, the probability of a matrix is just the product of the probabilities of the independent entries. If you have seen classical compact groups in Haar measure, the way number theorists like to look at this stuff nowadays is with Haar measure. Because then you have a natural notion of what does it mean to choose something randomly. I have a measure on my space of matrices. I have a group. The Haar measure gives me my notion of randomness. You could do this classically as well, and most of the research I do with students are looking at these classical ensembles. There's a lot of interesting stuff here. I talked a little bit yesterday how if you require your probability to be unchanged under orthogonal changes of variables, which basically just means physics should not change if I rotate my hands, that forces your entries to be a Gaussian. And for the first 40 years of the subject, we could basically only do things for Gaussians for some of the questions. Now we can do it for almost anything. Explicitly, what's the probability I have a matrix where the entries aij is in some interval alpha ij, beta ij? I just integrate my density from alpha ij to beta ij for each one of them, and then I take the product. Okay, so eigenvalue distribution. So we have the Dirac delta functional. Think of it as a point mass. So all of the mass is concentrated at 1 point. So if you want, the probability is 0 everywhere except at 1 point where it goes up to plus infinity, and the area under the curve is 1. You can often do this by taking a non-negative function and then just basically compressing it. So if you integrate any nice function against the delta mass, centered now at x0, you just get the value of your function at x0. And so what we're going to do is we're going to attach a probability measure to each matrix. So to each matrix, we associate a mass of size 1 over n at each normalized eigenvalue. So when you see something like 2 root n, the question is, where are the 2 and where are the root n coming from? The root n is far more important than the 2. The root n is telling us how things change as the size of the matrix grows. The 2 is just so I can use the word circle rather than ellipse later in the day. It's not as important. And so if I want to calculate how many normalized eigenvalues do I have in an interval a, b, I just integrate my density from a to b. I get a 1 over n every time lambda I of a over 2 root n is in the interval. So this is going to just count how many normalized eigenvalues live in a certain range. And then the kth moment of my distribution, I would just integrate x to the k times this. And so now instead of getting 1 over n, I would get 1 over n times lambda I over 2 root n to the kth power. And we'll see the eigenvalue trace lemma in a moment as to how this connects. All right, so Wigner's semicircle law is that if you have n by n real symmetric matrices, entries are nice, then the normalized eigenvalue density converges to a semicircle for almost all matrices in your system. Obviously, it's possible you could choose a diagonal matrix. It's possible you could choose a matrix where all the eigenvalues are 1 and you have a huge degeneracy of 0. But the probability of having that or something close to that is going to 0 so rapidly that almost all matrices will be very close to this. So here's the proof. So we use the eigenvalue trace lemma that the trace of a to the k is the sum of the eigenvalues of a to the k. And now the trace is just going to be a nice polynomial in the matrix elements. So the trace is just the sum of the diagonal elements. So what's nice about this is we're choosing the entries of our matrix, randomly. So we should have some hope of being able to understand a sum like this. And then this is giving us essentially the kth moment of the eigenvalues. I should multiply by 1 over n. I can multiply by 1 over n. Not a big deal. And the hope is that if I understand the moments, I understand the distribution. This is not always the case in probability. You can have two different distributions that have the same moments but are not the same. This is quite annoying. Some of you may have heard of a paper, can you hear the shape of a drum? Can you have two drums with different shapes that have the same harmonics, that give the same sounds? Unfortunately, the answer is yes. So this is where you sometimes have to appeal to advanced abstract nonsense that says, I'm in one of these nice situations and I don't have to worry about this. All right, so let's see how this can help us. So the first thing is let's find what the correct scale is. So the trace of a squared is the sum of the eigenvalues squared. So by the central limit theorem, well, the trace is aij, aji. And each one of these is a mean 0, variance 1 distribution. So because the mean is 0, the variance is the same as the second moment. So each one of these is roughly of size 1. I'm adding n squared of them. I should get something of size n squared. I'm just trying to give you a rough heuristic right now. You can make this more rigorous and more precise if you want to. I don't want to. So the sum of the eigenvalues squared is about n squared. So the sum of just the eigenvalues on average has to be, also n times the average of the squares is n squared. So the average is of size square root of n. Now one of the problems, of course, is I'm now passing, I've got the average value squared. So maybe these things are a little bit large and I'm getting some kind of cancellation in sign. So this is just meant to be a rough heuristic that you should expect square root of n is the size of the eigenvalues. So as the matrix grows, this is where you expect things to live. All right, so now here's the proof. Let's calculate the kth moment. So from what we saw before, it's the trace of a to the k over some powers of 2 and some powers of n. What's nice is if the eigenvalue is of size square root of n, we get some idea of how large this should be. And if we can ever show that a term in the numerator is smaller in power of n than the n to the k halves plus 1 in the denominator, it's not going to contribute in the limit, unless there's a huge number of such terms. So we want to calculate the average kth moment. So we have this quantity to do, and we want to show that this converges to the moments of the semicircle. The other thing you really need to do is it's not enough to know that on average things are fine. Let's say I want to show that things are converging to a half, and half the time I get 0 and half the time I get 1. On average it's a half, but nothing in the system is close to the average value. So it's not enough to show that the average is converging. You have to control the variance. You have to say, on average it's a half, and by the way, the fluctuations are tending to 0. Okay, well now if I know the fluctuations are tending to 0 and the average is a half, everything is going to be good. So if we substitute, here would be the calculation for the second moment. And this is deliberately designed to be misleading and to make you think that the subject is not that bad. So if I put in the second moment, I've got, I don't know why I write aji, someday we'll eventually fix this and write ij. So I've got integrals and sums. Can I switch integrals and sums? So I need some kind of convergence results to allow me to do this. You should be a little bit scared because we have, integrals over an infinite range, but I only have finitely many sums. And since I only have finitely many sums and all the integrals are going to be finite, everything is fine. If you put in absolute values, everything is fine. So there's no problem using Fubini-Tonelli to justify this. Whenever possible, you want to work with things that are finite. All right, so now when we do this, well, I move out the double sum. So I'm going to have n squared sums. And in each sum, I have one term in each polynomial. And all the other integrals are just going to be 1 because it's a probability distribution. And because I have mean 0, variance 1, this is going to be 1, so everything is 1. So I end up getting just 1/4. So it looks like it's not that bad. The further, whoa, stop going. The further you go, the harder it gets. Let's look at the kth, or the 2 kth moment. Or maybe this is the kth moment. So this is the kth moment. So now I would have something like this. I can pull out the sums again, and then the question is, when does a term like this survive and contribute? Well, since I have mean 0, if any of these are ever unmatched, it will just integrate to 0. So everything has to be matched in at least pairs.
What is matched?
The A's. So if I have A12, I have to have either another A12 or an A21 somewhere. Because if I have an A12 all by itself, it has expected value 0. And so when that hits the P of A12, dA of 12, it'll just be 0. Any A that occurs here, any pair of subscripts, I have to have that at least twice. And in some sense, this is beginning to see where the k-halves is coming from. You look somewhat confused. Okay, you're good? So I could have A12, A21, and then another A21. So I could have A12 cubed, and that would be giving me a third moment from the A distribution. It turns out that in all the ensembles, third and higher moments give you a lower order term. And this is from the counting on fingers argument that I've been talking about again and again and again. When you look at how many degrees of freedom you have, when you look at how many ways this can happen, you're dividing by such a high power of n that if you have 3 things that are all together and everything else matched in pairs, you don't have a high enough power of n to be non-zero in the limit. So this is just a calculation you need to do. If you have things matched in quadruples, it's even worse. So you basically need to know how many ways can I match things in pairs. So imagine you have, well, what can you tell me about k if you want everything matched in pairs? What must k be? K must be even. So let's write k as 2m. How many ways are there to match 2m objects in pairs? There's a really nice answer for this. Yeah, it's 2m minus 1 double factorial. So choose any element. You now have 2m minus 1 things left over. Choose one of those to match with the first element you chose. There's 2m minus 1 ways to do that. You now have 2m minus 2 things left. Choose one of those, and now there's 2m minus 3 choices for the next one. And so as you march down, you see it's 2m minus 1 double factorial. The double factorial means take the product of every other. This is actually the moment of a Gaussian. The 2mth moment of a Gaussian is 2m minus 1 double factorial. What this is essentially saying is, in some sense, the Gaussian dominates the density of states. If everything contributes fully, you get a Gaussian. As soon as things stop contributing fully, it's going to be something that's tighter than the Gaussian. The probability is not going to go off as rapidly. You're not going to have as much probability far away as a Gaussian. So here are some numerical examples. So here's looking at 400 by 400 matrices, choosing the entries from a Gaussian. The red line, if it's visible, is the theoretical curve. The blue histogram is extremely close to it. So this is just meant to show you that things look good. This is choosing a Cauchy distribution, one of my favorite distributions. Whenever you need a test of how robust a theory is, we move a condition and see what happens. We assumed the entries were independent, identically distributed from a nice distribution, mean 0, variance 1. So the Cauchy distribution 1 over 1 plus x squared, you can argue whether or not it has a mean. If you integrate x over 1 plus 1 over x times 1 over 1 plus x squared, if you want, you can say it integrates to 0 because it's an odd function. But whenever you have a integral from minus infinity to infinity, you now have to be careful. And the value depends on how you integrate to infinity. If you go to infinity in a symmetric way, you'll get 0. If you go from minus a to twice a, you'll actually get like the log of 2. So depending on how you argue, it either does or does not have a finite mean. It does not have a finite variance. When you integrate x squared over 1 plus x squared, that's converging to 1. Well, if I want my integrand to be finite, it better be going to 0. So the Cauchy distribution is a wonderful example to test how things go. What this means is not all of a sudden things have a huge blip at here. This is just how much mass is from this point onward. And so if you look, you should be able to see not a semicircle. Okay? I debated having a subliminal message in that, but that is technically illegal, I believe, in this country. All right. The GOE conjecture, which is now a theorem, is that if you talk about the spacings between adjacent eigenvalues, it converges to something that's approximately given by this form. And for a long time, we only knew this for Gaussian matrices. We now know it in greater generality. We're not going to look at this, but it's worthwhile for you to know what's out there. So here's looking at the uniform distribution, and here's looking at the spacings between adjacent eigenvalues. I am not plotting the correct theoretical limit for the solid curve. I'm plotting the close approximation that's within maybe 1 to 3%. It's just much easier than working with the determinant of the Fredholm operator. So we all lie like this. Good fit or bad fit? What do you think happens with the Cauchy? Good fit or bad fit with the Cauchy? Well, what do you think?
It's worse.
It's worse. Anybody know why it's so much worse with the Cauchy? How many of you read XKCD? XKCD is a very funny comic strip. One of my favorites is two people are dating, and one goes to the other and says, I think we should break up. I've done a statistical analysis, and presents their work. And the other person looks and goes, I agree, we should break up. And I thought this would convince you. I thought my analysis would convince you. No, 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 it's not your analysis. I think I can do better than someone who doesn't label their axes. Given that hint, why do you think the Cauchy is much worse than the uniform? Yeah, the Cauchy is 100 by 100. The uniform is 300 by 300. Always look at the axes. Always look at the labels. If you make the Cauchy 300 by 300, it's fairly good. Right? It's really easy to manipulate data. It's really easy to frame things. Okay? There was some talk yesterday about, am I doing things deliberately? Yes. And sometimes I will say what it is. But you want to be very careful, especially when you're reading political polls and stuff like that. There is a lot of work that people do to manipulate how things are presented. So what this is telling you is that the spacing between events is more universal than the density of states. So you can also look at graph theory. And so have a bunch of vertices, and then Aij is going to be the number of edges connecting I and j. Most of the time we'll look at graphs that do not have compound edges. So here I've got multiple ways of getting between 3 and 4, or getting between 3 and 4. Think of it as maybe it's extremely important that 3 and 4 can communicate. Maybe it's the president and NORAD, and you want to make really sure that you can launch the nuclear strike if you want to. Or maybe I want to have multiple ways to reach Papagino's Pizza to have another large order for you guys to get food. So sometimes you might want to have multiple paths. Most of the matrices we look at, it's cheaper not to have multiple paths. And you can look at the density of states. So here is what you get when d equals 3. So what this means is each vertex is connected to exactly 3 others. Does this look like a semicircle? No. However, let's look and see what happens as d gets very, very large. So the eigenvalues x is at most basically 2 root d. When d gets very, very large, x squared is of size d, so d squared minus x squared is about d squared. So this is about a 1 over d outside. So this becomes a constant, and this becomes a semicircle. So as d goes to infinity, the d regular graphs converges to a semicircle. So here's d equals 6, which looks a lot more like a semicircle. If you look at the spacings between eigenvalues of 3 regular graphs, you again see this GOE distribution. And so what I like is this is a graph by 4 people, including Steve Miller, but not myself. So my thesis advisor is so good he's lapped the alphabet, and I'm his second student named Steve Miller, born same year, same city as the other. He was kind enough to allow me to use this image. All right, so now it's time to get to the real stuff. So let's look at real symmetric Toeplitz matrices. This is the first ensemble I looked at with students where we got new publishable results. So a Toeplitz matrix, we talked a little bit about this yesterday, is constant along diagonals. So you have essentially on the order of n degrees of freedom. Whenever you're doing talks like this, you're often a little bit careless, and you say, it's order n. Technically, it's n minus 1 degrees of freedom here. I'm going to probably set b0 to b0, because all that does is just shifts the eigenvalues by a constant. But maybe I don't want to. Maybe it's easier to have b0, not 0. It just depends on how you want to define things. So this ensemble, this set of matrices, has far fewer degrees of freedom than real symmetric. Real symmetric is order n squared over 2. Maybe this is enough so it has very different behavior. So we form the eigenvalue spacing measure exactly as before, to count how the density of states. The kth moment I'll define as mk of an. This notation is a little bit overkill. A is going to be an n by n matrix. I don't need to put the n there. I like to put it there so I remind myself what is varying in the problem, and to remind myself that this depends on n. And then mk will be the limit as I average over all the matrices and then send n to infinity. So it turns out the 0th moment is always 1. The odd moments you can very easily show are 0, and the second moment you can show is 1 without too much trouble. You want to start calculating the 4th moment. So more generally, now instead of the a's, I'm going to just write it as b's. All that matters is which diagonal you're on. So if I minus j is 0, you're on the main diagonal. If I minus j is plus or minus 1, you're immediately above or below the main diagonal, and so on and so on and so on. So I need the b's to be matched in pairs. So when I look at it like this index must be the same as this index, or it must be the negative. So there are two possibilities, right? It turns out that the only one that will contribute is when all the signs are minus. And this is just a calculation you go through. I don't want to go through it now, but again, it's counting on fingers. And to just say that if you ever had one of the epsilons that was not a negative sign, then you would actually get a linear dependency and you would lose a degree of freedom. And when you lose a degree of freedom, now you're dividing by a higher power of n than the contribution, and it will go to 0. So it all just comes down to just a little careful bookkeeping. It's one page in a Beamer presentation to just do the calculation. Okay, so all the terms have to be negative signs. That's great. So the maximum contribution we can get would be 1 if it contributes fully. And so we know that the moments are bounded by the moments of a Gaussian. So the question is, do they all contribute fully? And the original conjecture was yes. Turns out the answer is no. So there are 3 possible configurations. Here's ij, jk, kl, and then get back to li. I can match ij with jk, and then these are matched. I can match across. How many configurations are there really? So I've drawn 3 pictures, but how many are there really? 2, right? This one is really the same as this one. So when you're doing these analyses, you want to look at how many different shapes do I have? And this becomes an interesting question. How many distinct shapes can you have when you're matching things in pairs? What's going to matter in a lot of these ensembles is whether or not there's a crossing. If you've heard of Catalan numbers, the Catalan numbers are the number of ways of matching things without crossings. And the Catalan numbers turn out to be the moments of the semicircle. So for the full ensemble of real symmetric matrices, if there's a crossing, it doesn't contribute. It's a nice calculation. So I want to calculate what's going on in these 3 cases. So case 1, x1 equals x2, x3 equals x4. So I believe that's this case. And so I have I1 minus I2 is minus I2 minus I3, and I3 minus I4 is minus I4 minus I1. So when the dust settles, I've got a minus I2 on both sides. I1 equals I3. On this side, I've got a minus I4 that cancels, and I get I1 equals I3 again. So I1 equals I3, and I2 and I4 are completely free. So how many triples do I have? I have essentially n cubed triples. Remember, I want things matched in pairs. If I have this equals this, and this equals this, and this value is the same as this value, all 4 things are the same. And that's not going to be a second moment now, it's going to be a fourth moment. That will be a lower order term. So there's really only n ways that that happens. Of the n cubed things, it's insignificant. But technically, you've got to be careful, because if they're all matched, I'm not getting the square of the second moment, I'm getting the fourth moment. So I will get a contribution in the limit of n cubed. Minus n times I get 1, n times I get the fourth moment, so in the limit I get 1. Great. Now let's look at see what happens if we have the cross term. So now x1 equals x3 and x2 equals x4. So now, when the dust settles, you get I1 is I2 plus I4 minus I3. One of the things I really love is just trying to get an estimate, a feel for what the answer is. You can calculate how many times will you have quadruples between 1 and n that will satisfy this equation. All I want to do right now is show that it's not n cubed in the limit, that it's less. If I2 and I4 are large and I3 is small, then I1 will be outside the range. Similarly, if I2 and I4 are small and I3 is large, then I1 will be outside the range. So for example, if I2 and I4 are at least 2/3 n and I3 is at most n/3, then this number here is going to be greater than n. Well, my index has to be between 1 and n. So what this tells you is at least 1 out of 27 times one of my triples will not give a valid I1. And so it's not going to contribute fully, it's going to contribute less. How much less? I don't know. But it will contribute less. Well, okay, I do know. You can do the calculation, it's not bad. You get 2/3 rather than 1. And here's your curve. So I think I was at Princeton, so I was trying to choose Princeton-ish colors here. Does that look like a Gaussian? If I showed you this without telling you that it's not a Gaussian, would you have said Gaussian? Yes. Okay? So both our group and another group that was independently looking at this, we both wrote down, it's a Gaussian! And then we did oh, it's not a Gaussian. So if you look at the tails really closely, you can see the tails are decaying too rapidly. But it's hard to be looking at it that closely. So we proved that it's not a Gaussian. We proved a lot of results about how rapidly it converges. If you look at the density between adjacent eigenvalues, you don't see the GOE distribution, you see Poissonian behavior. Very, very different system. I'm not going to go through the real symmetric palindromic Toeplitz matrices. That may be the longest named ensemble we've studied to date. No, we have the highly symmetric, I think. No, we have the highly palindromic. I think that beats it by 1 letter. But basically, it's just putting in a palindrome in the first line. And that gives you extra matching. So for instance, now, before if I was B1, to be matched, I would have to be either on this diagonal or I'd have to be down here. And it turns out you always had to be down here. But now that it's palindromic, I could also be here or down here. So it gives you more possibilities for matching. And it turns out that that fixes the problem of the index being outside the range. So by putting in this palindrome, now you will always get something in the range. So I'm not going to go through the details. You actually end up getting a central limit theorem out of this, which is kind of nice. So the real symmetric, highly palindromic Toeplitz matrices was, well, what if we make the first row a double palindrome or a quadruple palindrome? How does that affect the limiting behavior? What can you get? So I will just go through this. I'm not even going to say anything, but you can always hit pause or look at the slides because now it's over there. All right. This is one of my favorite ensembles. I'm going to skip the weighted Toeplitz. I will talk about the block circulant ensemble. And so this is one of the few ones where we actually have a nice thing in closed form expression. So when you are doing talks, make your slides useful. Make your slides helpful. One of the things I hate is people who gray out slides. Have you seen this? Where it's like in a light gray and you're not supposed to really be looking at it, and then the presenter toggles forward and the gray becomes dark and you can see things. What do you do when you see something that's light gray and you're not supposed to look at it? You look at it, right? Hide things, right? So in tech, you can have a pause command, you can have an only, where you display just certain things. You want to control what information is on the slide. The more information on the slide, the more time they spend looking at the slide and the less time they spend listening to you. You want to use color well to illustrate what's going on. I want to talk about something on a wrapped diagonal. All right, so I'm going to have all my matrix elements black, but the diagonal I care about, I'm going to alternate colors red, blue, to make it really clear. So I'm looking at now an 8 by 8 symmetric 2-block circulant matrix. So, here's this block over here, and then I notice I have the same block here, same block here, same block here. This block here then moves here. You see it's moving around. And so you can look at various structures over here. And so each diagonal is now periodic with period 2. And you can do the exact same calculations as before. And I want to have things matched in pairs. And when I have things matched in pairs, all that really matters is how often do I have a second moment term, how often do I have a fourth moment term, how often do I have a sixth moment term, and so on and so on and so on. So I have over here my various moments. And so there's a nice topological way of looking at this. I'm not going to go into too much detail right now, but here are my indices, and I can identify the edges. And depending on how they're matched, that either means they're in the same orientation or opposite orientation. This is another way of looking at the plus minuses and seeing some algebraic geometry coming into play. And all that really matters is they've got to be oppositely aligned to contribute. And so the only ones that are matched in opposite directions, and then it becomes a question of how many ways can you do this? So it turns out that this is equivalent to certain problems in counting. Since we are probably not going to look at this ensemble, I'm just going to have the slides flash up here. There is stuff available. There are generating functions to get the answers here. There's a lot of tricks and techniques you can use from complex analysis to pull these things off. You might notice this term over here. This is the Gaussian stuff over here. And this is a depressing factor. And so we end up getting, using some complex analysis, we get an explicit form for the characteristic function. So different areas of mathematics have different accents. So a number theorist will say a Fourier transform, a probabilist will say a characteristic function. They're almost the same. There might be a slight change in terms of where you put your pi's or your 2 pi's. It's really the same thing. If you know the Fourier transform, if you think is nice, you can take the inverse Fourier transform and recover your function. And so this gives us the Fourier transform of the density. We can then go backwards and get the actual density. And if you notice, here is a Gaussian. And here's a bunch of other weighting factors. And it turns out as m goes to infinity, the limiting spectral density approaches that of a semicircle. Well, if you think about what's happening as m goes to infinity, m is the length of the period. So the shorter m is, the more structure you're imposing on your matrix, the more likely it is that you're going to see very different behavior. The bigger m is, the less restrictive of a condition this is. And so what I like is, this is what's going on with m equals 1, 2, and so on and so on and so on. And you can see we're actually able to capture even the little fluctuations. So it's remarkable how quickly this goes in. So there's lots of other things you can do. This gives you a sense of the tools and techniques for problems like this. And then the goal is to apply this to other ensembles. So the Toplitz paper is a great paper to read. It does all the calculations in full detail, and then future papers say you're arguing as in this paper, one sees for a lot of the abstract nonsense you need to just show that the convergence is okay. Okay, any questions about random matrix theory right now? Okay, could somebody hit stop?